So I'm here today, as you know, to talk to you about video for Linux. And I would like to get a bit of a feeling about your interest here. So a quick show of hands, if you could raise your hand, if you're here mostly because you're interested in video for Linux, because you implement drivers in the kernel that expose the V4L2 API. Maybe between a third and half of the room, okay. How about you use video for Linux in user space? More people, and a bit of an overlap indeed. Did you sit in the wrong room? Okay. Not too bad. Well, if you want to have a nap in the back, that's fine. There are free seats. We'll start with a little story, actually, that didn't happen that long ago because it's something that's happened to me yesterday. I was going around the booth downstairs, and someone came to me and said, you know, what do you think about video for Linux these days? Is it really suitable for cameras? I thought, okay. Now I know that what I'm going to tell you today will probably be useful to someone, except I don't really see him in the room. So, too bad. We'll start with, I'll go through the talk with a list of misconceptions about video for Linux. And the very first one is misconception number 1. V4L2 is a webcam API. Who agrees with that? V4L2 is just a webcam API. Right, 100% right answer. Obviously, it's not. Otherwise, I wouldn't be here today. We would be done with the talk. So we'll look at a bit more interesting hardware here. That's going to be, I see Marek frowning over there. I know it doesn't show anything RenderSS related. I'm sorry. No, so the hardware we're going to talk about is a bit of a mix of different components because it's cameras. Obviously, we have camera sensors. And I wanted to throw in the middle serializers and deserializers. So something that you see more in automotive use cases and not necessarily connected to Raspberry Pi. But that doesn't matter. Let's ignore that for a moment. And then obviously we have a board, we have an SoC, and we have the camera streams coming in, and lots of things happening inside with lots of processing. So there are only 2 cameras over there because I found that picture online, and I'm really bad at drawing stuff or modifying them, but I need 3 cameras actually. So here's an example of different bits and pieces. So we have 3 camera sensors on the left. They are raw camera sensors. I pick specific model names. We'll see later why. And then we do have serializers, so that you can transmit your camera stream over a longer distance, and a deserializer, to which you can connect up to 4 cameras. There's only 3 in this case. And all that is connected, in this example, to RenderSS SoC, and we capture frames to memory. Obviously, inside the SoC, we do have lots of hardware complexities. If you look a little bit more, there are a few components and IP cores in there. So we start with a CA-SATA receiver. We do have a unit. I'm not going to bother explaining all the acronyms because they're vendor-specific, but that's a big DMA engine that will write frames to memory. And then those raw frames capture from the cameras. They are processed by an ISP in memory-to-memory mode. So that leads me to my second misconception. So the hardware I just showed you looks very different than a webcam. And there are people who told me multiple times, you know, video for Linux is not really meant for that. And to that, I would just like to reply that we've been handling that kind of hardware for more than 10 years now. So there's still improvement that are needed. But we have, in addition to video for Linux, an API called the Media Control API. And that's how that API would expose the hardware to user space to show what's inside the device. So you should recognize more or less the different building blocks that I showed before, the blocks in green. Who's familiar with this kind of representation, a Media Control API? Should have us the other way around. Who doesn't know what that kind of graph is? Okay, thanks. So I'm going to explain that. So what you're looking at here, it's an automatically generated graph that represents the topology of the device as exposed from the kernel, by the kernel to user space. So we have an API that you can call from your application, and that allows you to enumerate the internal pipeline, the different building blocks that we call entities, and how they connect it through links. And that, in the end, represents that's the graphical view of that media pipeline. The blocks in greens are what we call in V4L Linux subdevs. They're processing elements mostly, while the block in yellow represent the interface to memory. They are the video devices, the classical V4L video devices, and in this context we use them to transmit data, read data from memory, write data to memory. This is not an actual graph of real hardware. I kind of made that up yesterday. It's, to my knowledge, as close as possible to the drivers we have upstream, but I'm sure there are a few mistakes if you see typos or towards on the right-hand side, 4 subdevs that are numbered subdev 10. That's because I was too tired and didn't notice it. But the Media Control API is about exposing, as I said, the internal topology of the device to user space. It's most of the entities that you see, as I said, are V4L2 video devices, the subdevs, and this API is complemented by the V4L2 subdev API. That's also an API exposed to user space that allows application direct configuration of all the elements in the graph there. I was actually shocked how old that was. That's before even V3.0, kernel V3.0. So we're talking about an API that was merged 10 years, sorry, not 10 years ago, 15 years ago in 2010. So saying that V4L2 was never meant to support these kind of use cases, well, for 15 years we've been trying to do that, and I think succeeding in many cases. That's widely documented, a bit of shameful advertising there to a document I wrote. So if you're not familiar at all, actually, with the subdev API, the media controller and all that, that's a very good introduction. That leads me to misconception number 3. If we agree that V4L2 can handle some of that, then there are people who could say, well, it can't handle all of it. That's going to be a bit more difficult to debunk because I have to prove that every single piece can be handled by V4L Linux. So that's what we're going to go through, and we're going to split that misconception in smaller ones. So misconception 3.1. V4L2 cannot handle CSI2 virtual channels and data types. Okay. So to go there, we'll first need to talk about what we call subdev states. That's also a concept that is relatively old. And in a nutshell, a subdev state is information storage about a subdev, so one of the green blocks you saw in the graph. And it stores the configuration of that subdev. It stores the format of the data that goes through the links. It stores the resolutions. It stores that kind of information. And those subdev states exist in 2 forms. You have an active state, which represent the active configuration of the device, what the hardware is actually configured for. And you do have a set of tri-states. So the tri-state is something you get for free when you open a device in user space. It's a state like the active one that you can modify, that you can query, but everything you do in there has absolutely no influence on the device. It's throwaway. It's for you to be able to try a configuration and see if it gets accepted and how you need to adjust it to make it accepted by the driver. So the benefits of the subdev state is that the small benefit is that it simplifies storage of information for drivers. Before subdev state, they had to store all that configuration in driver-specific structures manually. But with the subdev states, they can do that in a more centralized fashion, so the code is a bit simpler. But also, it's a really important building block for all the things that we'll see in the rest of the talk. So to use subdev states, that's originally an opt-in feature. So you have to call an initialization function at probe time. You have to implement an operation that's called init state. That's going to initialize your state. And after that, you can access the state from state pointers that are given to basically every subdev operation. So we're going to go through some code on the slides. I'm not going to spend lots of time on them. The goal of this presentation is really to give you an overview of the different APIs we have, and also to serve as a reference if you're interested then in looking that up and trying to learn more. So the code we have there is for that purpose. The links to different pieces of documentation will be for that purpose as well. So we'll go relatively fast on the different points because there's lots to cover. But the state, as I mentioned, it simplifies drivers. So there's a bit of a bonus point there. There's one of the subdev operation called getFormat that drivers originally had to implement manually and return the current format that's configured on the device. If you use states, then you can use a helper provided by the core. So anything that in the examples has a V4L2 prefix in function names is core helpers that are not implemented manually by drivers. You access state data, or the configuration of the device, from the state. So you have a set of functions to which you pass a state, and they give you a different piece of configuration, as I said, the format, the crop rectangle, and things like that. And the V4L2 core also takes care of locking. Because you don't want user space to be able to modify the configuration of your device concurrently to starting a video streams, because those two operations could lead to invalid configurations and breakages. And so the locking that was usually done manually in drivers now is centralized in the core as well. So simpler for drivers, less bugs. One thing that we don't have in the states yet is storing the value of V4L2 controls in there. So we have format, selection rectangles, and other pieces of information, but not the controls yet. And so to make things work, you need to make sure that you use the same lock for the state and for the control handler in your driver. So that's those two lines of code. Well, the first one, actually, that assigns a control handler lock to the state lock. So if you do that, you're fine. All the subdev operations that are called and that get a state pointer are guaranteed to be called with the state lock, so you don't have to handle the locking manually. There's one particular operation. I mentioned that controls are not handled by the states yet. So the set control operation doesn't get a state pointer, and if you need a state in there, you have to manually get it. So there are functions as well to be able to get the active state of the device. There are still a few corner cases where we could possibly have deadlocks when things are, well, not because you implement your driver incorrectly, but in some use cases, that's something that we're working on and it's going to be fixed. So there's documentation in the kernel documentation this time. So that API I mentioned is still relatively early, introduced in 6.2, much newer than Media Controller, but still. It's now, I consider that to be mandatory for new drivers. So if you write a new driver, use that. Not all drivers do it, because not all of them have been ported to that, but it does simplify drivers. And as I said, we don't have support for storing controls in there, so I'm not going to ask for a show of hands to see who would volunteer to implement that, because I would be very sad. So I will cling to this impression that most of you would like to help. We'll also plan to work on the ability to subclass a state to be able to store driver-specific information in there. So let's go back to virtual channels and data types. I actually have to talk about streams first. Yeah, I'm sorry. That's, if I recall correctly, that's the last time I do that. After that, it's really going to go to virtual channels and data types. So what's a stream? I've quoted there two pieces of documentation we have in the kernel, very useful. So a media stream is a stream. Thanks. In another part, it says that a stream is a stream. I'll try to be slightly more helpful than that. So the concept of streams is that we wanted something that would model the flow of data through a media graph, so the graph that you saw earlier. You see you have entities, they have paths, they're connected through links, and we needed something to be able to show where the data originates and where it goes to. And so streams are deeply related to the concept of routing in the graph, and especially inside subdevs. So when data comes in a subdev, where does it go to internally, and where does it exit from, and what happens to it? And it's also very related to handling stream multiplexing, which is the ability to carry multiple of those streams over a single link. And that's something we need for CSI2, virtual channel data types, because at the hardware level, CSI2 does just that. So subdevs with this API now have an internal routing table. We had a graph with links between subdevs and an API in the media controller to be able to control those links, enable, disable them. Now we have an API to be able to set a routing table inside a subdev. As I said, we can multiplex streams over links, so each pad can carry one or multiple streams. And they are identified by just a stream ID. So the stream IDs don't have any particular significance. They're local to a link, in the sense that if you look at a link between two subdevs, connecting two pads, if you have multiple streams going over that, the stream that's number 3 on one side of the link is going to be the same one that's number 3 on the other side of the link. But that's it. So the table is exposed to user space through an IOCTL. That's extremely interesting. As I say, it's a routing table, so it has a source and it has a sink, and each source is a pad in a stream, each sink is a pad in a stream, and you have a number of those. And so inside the kernel, the routing table is applied to the device by a new subdev operation. So your driver has to implement that to configure the hardware based on your new routing. The important part to understand is that it's the act of setting that routing table that will create the streams. So initially, the drivers don't know what flows through the graph because they don't know what you want to do. And so when you set the routing, when you tell what goes where, at that point, for every route that's created, the kernel, drivers, and the core infrastructure in Video for Linux will remember that you set different routes with stream IDs, and then we will use those streams at later points in the API. So because we can have multiple streams over subdevs that can carry different types of data in different formats, where we had formats that was stored in the state for each pad, now we have formats stored in the state, not just for each pad, but for each combination of pad and stream. So we have a more detailed view of what goes there. And the accessor functions that I showed earlier that allow you to get a format or a crop rectangle in a state now take a stream ID as well in addition to the pad number. Setting the routes is, from a use space point of view, the first operation that you have to do, because I said it creates a stream, so you need that to be able then, after that, to configure those streams. And that also means that when you set the routes, it's going to reset all the formats on all the pads in your sub-devices. So that's a kind of destructive operation. You start with that, and then you configure the rest. So in the implementation in your driver, when you implement the set routing function, you store the routing table in the state, you reset the formats, you have to validate what user space gives you to see if that routing table is acceptable. We have a helper function that can help with that. There are functions to be able to set that information inside the state. You don't have to do that manually. And most of the user space IOCTLs for subdevs now take a stream ID as well. So where they used to take just a pad and information about what to configure on that pad, they do take a stream now. We have a new set of helpers to be able to follow the route inside a subdev, because that's a very common operation when you go through the graph in drivers and see what has to go where. So we have a macro that allows you to iterate over all the routes and find the opposite end of a route, where is it connected to inside a subdev. So that's also documented in the kernel API, mostly in the header file where they're defined. And routing is an opt-in feature for drivers, because not all drivers use that. Not all drivers need streams and multiplexing of streams over a pad and a link. So if you need that in your driver, then you set a flag to say, yes, I opt into that. And in that case, we have an set stream operation, S-stream, very badly named because that one is about actually starting the device. So what we call start streaming in ancient Video for Linux law. And it clashes a little bit with the name streams now. So this S-stream operation that becomes deprecated, and instead you have to implement enabled streams, disabled streams in your driver. That gives you more information, it gives you the state is passed to those functions, it makes it easier for drivers to implement that. And also, you must never call those subdev operations manually inside drivers in the kernel. So when different subdev drivers communicate with each other, instead of calling the operation directly, you have to go through helper functions, because now the V4L2 core will keep track of information, and it has to update that information when those operations are called. That was introduced just one kernel release later, 6.3. It is disabled by default because we consider it to be experimental. So there was a patch that was merged at that time. So if you want to use streams, you actually have to patch your kernel and modify one variable from false to true, or the other way around. And so streams in the media pipeline, how does it look like? Well, now I can explain what happens, for instance, in the deserializer over there. So that block here, you see, has 4 inputs. 3 of them are connected to different cameras. And that device has the ability to configure, well, what camera stream goes where, to enable, disable them, to output all of them on the output CSI2 bus, or just block some of them and enable a single one. So using the routing API, you can now do that. In a different device, not this one, we could have a DM engine at the very bottom that has, well, lots more DM engines, being able to capture images from multiple cameras at the same time that are all carried over the same CSI2 link. And in that case, the subdev that we see at the bottom there, the subdev 8, would also implement the routing API to tell which stream goes to what video device. I promise we'd go back to virtual channels and data types, and I didn't lie this time. So virtual channel data types, they just model as streams. That's a fairly good match, and well, the streams in the API were modeled after that, so not a surprise, it was a good match. And as I said, a CSI2 link can carry multiple streams. The value of the virtual channel and data type, they have numerical values. They're not exposed to user space. They're handled purely inside a kernel. So if you are hard-coding them in the device tree, for instance, to configure a device and telling what virtual channel to use, you're not doing it right. If you take the stream ID that is passed in the routing table and say that the lower 8 bits will be the data type and the upper 8 bits will be the virtual channel, you're not doing it right either. Those are, at the moment, not exposed to user space at all, so there's no correspondence between stream IDs, the numerical values, and the numerical values of virtual channel and data types. Instead, those values are communicated between drivers. So we have a subdev operation called getFrameDescriptor that exposes a frame descriptor, which tell what's inside a frame. So if you think about your sensor outputting an image, the frame descriptor would explain what's the content of that. And if there are multiple parts in that image using different data types, if you have multiple virtual channels, they will be exposed by the frame descriptors. So we can see here that the frame descriptor at the bottom is just an array of frame descriptor entries. Each of them refer to a particular stream, so that's how we match to the stream ID in the routing. And for CSI2, they also have a virtual channel and a data type. So a sync device will be able to query from the source the virtual channel data type that it uses for a particular stream. So, well, we went through most of that already. The frame descriptors assume a line-based structure in a frame. So you could have a few lines at the beginning of the image of embedded data. That's a term in CSI2 that refers to metadata about the image that will be transmitted. A few lines of optical dark pixels, pixels that are shielded from light, but that you can still capture, and that allows you to calibrate your camera. Obviously, lots of lines of image data. But anything that's horizontal, like columns on the left and right side, those are not described by the frame descriptor. It hasn't been needed at the moment in the API. Maybe it's something we'll do later. So back to the media graph there, I said that the virtual channel data types are handled inside the kernel, so they are communicated between the devices. We have, does this still work? Yes. Yeah. So we have the cameras at the top and the serializers that will expose through the getFrameDescriptor operation what virtual channel they use. We do have the deserializer that has the ability in this case to remap the virtual channels. So if all the cameras output the images on virtual channel 1, each of them, the deserializer will be able to map that over the CSI2 link to virtual channels 1, 2, 3, 4 for the 4 cameras. If we didn't have that, we would probably need a way to dynamically allocate virtual channels for the different cameras. It's not something we have today in the kernel, possibly for the future. So, I mentioned sensor-embedded data. Next misconception, V4L2 can't handle that. Well, I just explained that it can. But very briefly going through that, CSI2 embedded data, lines of metadata at the beginning and the end of the frame. And so that's modeled through streams. If you have a sensor that has that, you have one image stream, one embedded data stream, great. You create them through the routing table. The DT values for those, the virtual channels, they expose through the frame descriptor, and you configure the formats through the operations we've seen before. And there's actually a problem. Now let's see who's following. So I mentioned that the streams are created by the routing tables that define how inside a subdev you route data from the sink to source. So if you have to create those streams on the sensors, well, they have just a source pad. How do you route things? What's routing table? There's no input to those. And so we had a problem there, and that led to, again, a new concept, the introduction of what we call internal pads. So it's kind of reusing the concept of pads because they're useful and everywhere in the API. And an internal pad is just like a pad, except that you cannot connect it with a link to something outside of your subdev. It models the ultimate source of the data inside a subdev. So it models the pixel array, for instance, that generates the pixels. You can use them in the routing table inside your subdev. That's how you create your streams. You can query the format. You can set the format. You can configure them inside your subdev, but you're just not allowed to connect them to something external. And so they identify by a flag that says that those are internal pads. And those open the door to lots of interesting things that we want to do and lots of creative use and abuse. And we were really concerned that we would be facing a big uncontrolled epidemic of creativity. And I think as software engineers, you know what happens when people get creative. If you get creative, it's good for you, but when other people get creative and you have to handle that situation, that's usually when, well, let's not start cursing and using bad words. So we knew we had to standardize things, but we also knew that those internal pads are very versatile and could be used for lots of different things. And so if we standardize them for one particular purpose and to be used in one particular way, that's going to close the door to lots of interesting things too. And so we introduced, again, a new concept, which is the subdev configuration model. So the idea is that we tell user space, through a read-only V4L2 control in this case, that a particular subdev exposes a particular configuration model. And the configuration model is just a piece of documentation that says a subdev compatible with this model will use streams in this way, will use internal pads in this way, will have this number of internal pads that represent this. If you set a crop rectangle on this particular pad, that's what it's going to do on the hardware. So it's really creating classes of devices. Before that, we had creativity in drivers. We had drivers using the API elements in different ways, and user space had no way to know. So writing generic user space was very difficult because you could have two sensor drivers that implement the same API with different effect on the hardware. Now, with the configuration model, we can finally have more generic code in user space. So we have one configuration model at the moment. That's a common row camera sensor configuration model that defines at least two internal pads, one for image data, one for embedded data, and a source pad towards the outside. It documents how formats and select rectangles are used for those. When you use that, when you implement the configuration model, you also have to use a new set of row media bus codes. We also introduce new row pixel formats. Traditionally in Video for Linux, we would encode in the pixel format the buyer pattern that was used by a sensor. That was a historical mistake, so we're fixing that with this new API. And because user space still needs to know what's the buyer pattern that is being used, we expose that through a V4L2 control instead. Work in progress, V11 of the patch series. Michael, I'm beating you with your V10 of your rock chip. Well, okay, it was really V24 for you, so you're still winning. So that's on the list. Great time to review that because it's getting close to being merged, but I'm sure there's lots of corner cases that would benefit from external eyes. So yeah, if you have a bit of time. So we saw embedded data, we can do that. How about HDR sensors? That's a bit more work in progress there. We don't have anything that's really implemented and working fully yet. There's lots of type of HDRs. Do you have multiple exposures or multiple gains? Is that line interleaving? Is that applying on different frames? Do you stitch your different frames with different exposures inside a sensor or in the SoC inside an ISP? So we're focusing at the moment on sensors that don't stitch the data, but output all the multiple exposure, multiple gains, line interleaved. That's the main focus. And we model that just with streams. You have 2 exposures, that's 2 image streams. That's it, easy. We still need a set of new controls that are being discussed, because if you have multiple exposures, well, you have to set multiple exposures. Right now we have a control that's a set exposure. Now we need multiple ones, and same for the gain, and same analog gain, digital gain. So we'll see how that goes. There's an RFC that was posted by Miralab from an XP. There's ongoing discussion, so also a good time to make sure that your use cases are covered. How about sensors with integrating NPUs to make things more complicated? If you're wondering, that does exist. That's a Sony IMX500, so it's a Sony sensor, and inside the same chip, you have an NPU connected to the sensor. Lots of work to support that, but very basically, the tensors that are going to be output by the NPU and transmitted over virtual channels and data types, they're just streams. Done. In reality, it's way more complicated because you have lots of things to control about the NPU, and V4L2 didn't do that in the first place. So it has to standardize new controls, new V4L2 controls, possibly new other things. But when it comes to routing the streams, it's exactly the same thing that we've seen before. There's a presentation, I think it's later today at 4:20 from Sony about the IMX500 and on how they open sourcing their camera stack, or rather the framework around the NPU for those camera sensors. So if you're interested in that topic, you can go see them. And that leads me to the misconception, and I see time is running out, so we're getting there. Misconception 3.3. V4L2 can't properly handle ISPs. So we're talking about the sensors, serializers, deserializers, all those streams, but the ISPs themselves, no, V4L2 can't do that. My reaction to that is pretty much this. Seriously. We've been implementing ISP drivers in V4Linux for nearly 15 years now. So yes, we can do that. We have API elements. We can have a media graph with multiple video devices. You can send raw images to your ISP. You can capture process images. That's what V4Linux does. ISPs need lots of parameters. We put them in buffers, and we give that buffers to the ISP through also a video device. We have an API to manage buffers and queue them and dequeue them for images. Well, we put metadata and parameters in those buffers instead. So we can configure the ISP that way. ISP produce statistics. We capture the statistics. We put in buffers as well. So all that is working today, and we have multiple drivers upstream that are using that. This supports both inline and offline ISPs, so what we call inline ISPs, ISP that connected directly to your CSI receiver and the camera sensor. There's no memory buffer in between. Offline ISPs are memory to memory, so you first capture the raw frames to memory, and then you have to process them in a memory to memory fashion. Last misconception, DRM would be better suited for ISPs, really? Because, you know, DRM, that's GPUs, that's accelerators, those are devices that process images, and what's an ISP if not something that processes images, right? So that's a loaded question and now that's going to be my personal opinion, with a bit of an agenda. So I believe that people who push for that do so because they think they could get away without documenting most of the hardware. You know, can I have a driver that they can upstream, that's fine, but without documenting the user space API and having just a user space closed source blob, and maybe not that bad, but we do have some disagreements when it comes to that. So, well, first of all, technical arguments. DRM doesn't support camera sensors. It won't. Nobody wants to do that. The pipeline with the streams, that complicated. We don't know how to do that in DRM. So any inline ISP that's connected to a sensor, DRM couldn't support that. Offline ISPs, memory to memory, that's, yes, a bit closer to the GPU, perhaps. But it means that if your ISP can operate in both modes, well, what do? You implement a DRM driver to operate it in memory to memory, and then a V4L2 driver for the same ISP in inline mode. Doesn't really scale. Those claims, I think, are mostly about not wanting to document features of the ISP. So on the technical side, there are things that were lacking until recently in Video for Linux, and it's support, for instance, for multi-context. Multi-context is the ability to time multiplex your memory-to-memory ISP between different cameras. That's something that we didn't really have. DRM doesn't have that either, but you can implement a custom API for a DRM driver to do things like that. But it's now work in progress from my colleague Jacopo that was presented during the Linux Media Summit this year. There are slides linked there. There's a patch series on the list as well. Work is ongoing, and I think it's going to be merged in a not too distant future because it's getting in good shape. So multi-context in Video for Linux, as I said, it's about multiplexing and providing user space with virtual instances of the same physical device. Because we're a bit short on time, I won't go into too much details, but the slides of the presentation summarize that fairly neatly. It's a new concept. Context are things that we didn't have, so now when you create a context, that becomes a piece of information, a storage a container for information about your whole device. And if you open your device multiple times, you're going to have multiple of those contexts. The tricky part is that in Video for Linux, because we have sub-devs and video devices, very often to control a device, you have to open like 4, 5, 6, 7, 8 different device nodes in /dev, and being able to link them all to the same context require a bit of trickery and 2 new IOCTLs to be able to bind those video device contexts and sub-dev contexts to the main one. But there's no real black magic and rocket science in there. They're really similar to the sub-dev we're introducing as well, with the concept of a video device state, similar to the sub-dev state. They store information, they simplify drivers, they will allow some cleanups in the core of V4L2, but also they will open the door to lots of interesting new use cases in the future. I shouldn't have mentioned that because my plan was to keep that silent and get the video device state merged and then do the rest, but no, there's going to be more. The last one I want to mention, that's media jobs. So the memory-to-memory ISP we have here, that's a Mali C55 ISP. There's a driver posted on the list, so that's also an open one. And in this particular instance, when it's integrated in the Renesas RZ-V2H SoC, the ISP itself doesn't have a DM engine to be able to read raw frames. Instead, there's a separate IP core provided by the SoC that handles that. And because it's totally separate, it's not made by ARM, and it's made by Renesas instead, and they're just connected together in an SoC. In a different SoC where you have this ARM ISP integrated, you'll have different IP cores to do that. So now we have different drivers from different vendors for different IP cores that have to communicate together to handle not a stream of data from a camera sensor, but to handle multiple video devices. Reading from memory at the top, writing to memory at the bottom, 2 different drivers. That is something that was not initially supported in Video for Linux. We considered that all the video devices had to be orchestrated by the same driver, and the media jobs framework is an attempt to solve that. So without going again in too much details, it's really the ability to declare what a processing job is, what steps you have, what dependencies you have between those jobs, and then when those dependencies are fulfilled, then the core framework will schedule the job and execute the steps across multiple drivers. That's also something that was used as an argument to tell, Video for Linux doesn't do that, so we need DRM for ISPs. But DRM doesn't do that either. It would need to be implemented in DRM in a driver-specific fashion. So actually standardizing it in Video for Linux makes it better than implementing it in different ways in different drivers. Last few things. What about user space? Well, every new piece of API, we have to implement compliance testing in the V4L2 compliance tools. That's mandatory for anything new. So that's ongoing user space development. We also learn from historical mistakes where we only implemented new APIs in test applications. And obviously, if you write a test application for the purpose of testing new API, well, it's going to work great. But when you start using it in real-life application, you realize that the API is bad. So we're not doing that anymore. We have to test APIs in real use cases, and in particular for cameras and ISPs, that would be in lib camera. Is that all? Well, a few things for the future. There's lots of unscheduled work. We're thinking about a full scheduler for media jobs that could be shared with codecs and multi-context. A new version of the request API, which I didn't mention here. Fences to be able to synchronize at a lower level within the kernel or even at the hardware level between different devices. And a few more things. And more importantly, well, what would you like to see in Video for Linux that's missing? So we don't have time for questions, I'm afraid. We started a bit late due to the audio issues, but I propose that if you want to ask any question, we can just get to the hallway and leave the space to the next speaker. Unless is it time for lunch break, or is there a next session now? Next session, okay. So let's go to the hallway and we can continue the discussion. Thank you.